This is a video on section 10.4, hybridization of atomic orbitals. So, my friends, you've learned about Vesper theory, you've learned about valence bond theory. Let's take a look at the molecule CH4. Okay, so our carbon atom has 2 electrons in the 1s, and in the 2s it has 2 electrons, and in the 2p there are 3 electrons. Okay, so according to valence bond theory, we're going to need 4 orbitals with 1 electron in it each, so that the hydrogen atoms can come in, overlap their 1s orbitals with the orbitals of the carbon atoms. Okay, also, again, as we said, having 4 orbitals with 1 electron in it, and the hydrogens will overlap with their 1s and form the 4 bonds, and we'll get our CH4. Well, we have a problem. The first problem is that unfortunately we don't have 4 orbitals with only 1 electron in it. Carbon has only 2 orbitals with 1 electron in it. We need to get 4 altogether. So the thought is that this electron right here, or possibly the other one, moves over to the 2p orbital, change is its spin, right? So it becomes a positive spin. And what we now have is see if we can erase this. We did. We have 3 orbitals, 4 orbitals now, actually. 4 orbitals with 1, 2, 3, right? We have 4 orbitals, 4 unpaired electrons, and now the hydrogen atoms can come in. Let's see if we can erase some of this stuff here, like some of the numbers and things. Well, we'll get rid of some of this stuff. Anyway, now the hydrogen atoms can come in and overlap their electron in the 1s, overlap the orbital with the 3 2p's and the 2s from the carbon atom, and there you go. There's your 4 bonds. Okay? So by promoting that 1 electron and changing its spin, we get our 4 orbitals in the carbon atom that only have 1 electron in it, and then the hydrogen orbitals of the 1s can overlap, and we get our 4 bonds. Problem is this, though. There's some problems associated with this. If we look at this picture right here, we see that the s orbital in our carbon atom looks like this, right? And the p orbitals of our carbon atom look like this, and they're oriented on the x, y, and z axes. Now, since they're oriented on the x, y, and z axes, that means that all those orbitals are at 90 degrees to each other, with the exception of the s orbital, which is a sphere, which is everywhere, of course. But the individual p orbitals are at 90-degree angles to each other. So why is that a problem? Well, I'll tell you why that's a problem. If we go back and make this a little bit smaller, the problem is this. The bond angles in a methane molecule, we know, are 109.5, not 90 degrees. So, valence bond theory kind of doesn't really explain very well the bond angles. Okay? Well, maybe we add a little Vesper theory in there. You know, the electrons are kind of rotating this molecule around a little bit. But, you know, how well can these p orbitals be rotated? Okay, they seem to be pretty well established where they're at. And remember, we're talking about regions in space around the nucleus where there's 90% probability of finding these electrons. So can that be changed? Well, another theory has been developed that can help us to try to explain what's going on when it comes to something like methane. And that new theory, or not new to the world, but new to us, is known as hybridization. The idea is this, is that the 2s orbital of our carbon atom and all 3 of the 2p orbitals in our carbon atom come together and form 4, whoops, it moved, 4 new, come on, stop moving, alright, 4 new hybrid orbitals. So these 4 orbitals, the s and the 3 p orbitals of the second energy level, come together and hybridize. They form 4 new hybrid orbitals. They are 1 part s, and since they contain p, but it's 3 part p, we put a 3 here, and we call them Sp3 hybrid orbitals. For every 1 atomic orbital that goes in, 4 hybrid orbitals, or sorry, let's try that again. For every 1 atomic orbital that goes in, 1 hybrid orbital must come out. So you see that there's 1, 2, 3, 4 atomic orbitals going in. We have to get 1, 2, 3, 4 hybrid orbitals coming out. And so, my friend, for every 1 atomic orbital that goes in, you get 1 hybrid orbital out. Those 4 electrons are now distributed over the 4 hybrid orbitals, and now the hydrogens can come in and overlap their 1s orbitals with their 1 electrons in them and form those 4 bonds. And the beauty of it is, whoops, try something here, hang on. And the beauty of it is, my friends, we can't adjust the picture. Come on, picture. Yeah, we can do this. That sounds like fun. The beauty of it is, if I can get this picture to move. Well, maybe we'll have to get rid of this stuff here. Sorry. The beauty of it is that the 4 hybrid orbitals point to the corners of a tetrahedron. So 1 hydrogen overlaps here, 1 hydrogen overlaps here, 1 hydrogen overlaps here, 1 hydrogen overlaps here. And this is the shape of your hybrid orbitals. Your hybrid orbitals have a different shape. They have 1 big lobe and 1 little lobe. So they have 2 lobes, lobe number 1 and lobe number 2, just like p orbitals do. But the big lobe is for overlapping, and the little lobe really doesn't do much of anything. So you've got 2 lobes now. You've got a big lobe and a little lobe. And that's what they look like. And in Sp3 hybridization, they point to the corners of a tetrahedron, and we know that is the geometry of our good friend CH4, methane. And that's how this type of hybridization works. Perfect. There are other types of hybrid orbitals also, in addition to Sp3 hybridization. What are those types of hybridization? Well, there's Sp2 hybridization. In Sp2 hybridization, same idea. We're going to go back to that carbon atom with its 2 electrons here, and its 2 electrons, 1 in each of those. And the reason I'm drawing it like this is you can see that the hybrid orbitals are actually of an energy that's somewhere in between the s and the p. So they're not at the same energy as the s, and they're not at the same energy as the p. They're at an energy somewhere in between. So in Sp2 hybridization, we get 3 hybrid orbitals, because remember, for every 1 atomic orbital that goes in, you get 1 hybrid orbital. And one of the p orbitals, which doesn't hybridize, remains at the same energy as it was before. And the 4 electrons are distributed over all of those orbitals. Okay? Now, in addition to Sp2 hybridization, we can also have Sp hybridization. And again, back to that same carbon atom. 1, 2, 1, 2, 3. Boom, boom. There's our 2p orbitals. Right? Hybridization occurs. If it's 1 part s and 1 part p, that means 1 s orbital is going into hybridization, 1 p orbital, so we're going to get 2 hybrids. Because remember, for every 1 atomic orbital that goes in, you get 1 hybrid out. And those 4 electrons, again, are now distributed over the s and the p. And there's your Sp3 hybridization. Okay. So we saw that Sp3 hybridization was responsible for tetrahedral geometries or tetrahedral electron arrangement. Sp2 hybridization is responsible for trigonal planar electron arrangements, and Sp hybridization is responsible in most part for, whoops, I didn't want to say hybridization, I don't know why I wrote that, is responsible for linear types of electron arrangements. I know that we saw linear molecules in a different type of arrangement out of the subset of the trigonal planar, and so Sp hybridization is not really involved in that one. But for simple molecules like Ab2, that central atom is going to have Sp hybridization, and we have our linear molecules. And for our Ab3s and all subsets of our Ab3s, that's responsible for the trigonal planar shape. And our Ab4s, Sp3 hybridization is responsible for that. They're tetrahedral shapes. And so, my friends, we'll try to draw some pictures. Whoops. I apologize for this being kind of chopped up. I've had 20 million interruptions in this video. This is the second time I've tried to make this video, and the second time I've had 20 million interruptions. What we were trying to say is that when it comes to our different hybrids, they basically have the same shape as our Sp3 hybrids, and those are the dumbbell type where you've got the big lobe and the little lobe. They just point in different directions depending upon how they meet the needs of the geometry. And so your Sp hybrids, right, they're going to go and be linear. And your Sp2 hybrids, they're going to point to the corners of a flat triangle, and there's your trigonal planar. And we saw that the Sp3 hybrids, they point to the corners of a tetrahedron. Okay, we also want to review a little bit further, as we were saying, that Sp3 goes along with your tetrahedral arrangements. That's because you need 4 hybrid orbitals. So if you add up the total number of atoms bonded to the central atom and the total number of lone pairs on the central atom, if you come up with 4, you know it's Sp3 hybridization. Sp2 goes along with your trigonal planar arrangements, and that deals with 3 hybrid orbitals. And again, if you add up the total number of atoms bonded to the central atom plus the number of lone pairs on the central atom, if it comes up to 3, you know that's an Sp2 hybridization on that central atom. And of course we said Sp is with most linear molecules, and you need 2 hybrid orbitals. And so if you count up the number of atoms bonded to the central atom and the number of lone pairs on the central atom, if it comes up to a total of 2, then you know the hybridization is linear. There are 2 other types of hybridization, and those are the types of hybridization which we'll see with expanded octets. They now involve not only s orbitals and p orbitals, but they also involve d orbitals. And those 2 types of hybridization are Sp3d, and that gives you 5 hybrid orbitals. And if you add up the total number of atoms bonded to the central atom plus the number of lone pairs on the central atom, if you come up with 5, then the hybridization on the central atom is Sp3d. And again, if you need 5 hybrid orbitals, that expands the octet. And then there's Sp3d2, which has 6 hybrid orbitals. And again, if you add up all the atoms bonded to the central atom plus the number of lone pairs, you come up with 6. You know the hybridization on the central atom is Sp3d2. And this goes along with the trigonal bipyramidal arrangement of electrons, and this goes with the octahedral arrangement of electrons. Okay, I know this video is long, and again, I said it was before, it was kind of chopped up. But if you have any questions, see me or Mr. Walsh, okay? Have a good day.